Welcome. Here we're going to be looking at spring problems, particularly finding the work required to stretch a spring. So here, this first example we have is a spring has a natural length of 6 centimeters, a force of 7 newtons is required to hold it at a length of 14 centimeters. And then the question is, how much work is it to stretch the spring from 20 to 22 centimeters? So this is our problem statement. We're going to use Hooke's law for this. So Hooke's law is that the force exerted on a spring is equal to K times X. So this is the force function. It's the thing that we're going to integrate. I know, and then K is the spring constant. And the units on the spring constant are newtons per meter. And then X is the distance in meters from the natural length. All right. So because my formula requires that I have K is newtons per meter and X is the distance in meters from the natural length, the first thing I'm going to do is go back and change all of my units were given to me in centimeters, and I'm going to change all of those to meters. So I'm going to change 6 centimeters to 0.06 meters. This will be 0.14 meters. 20 will be 0.2 meters, and then 0.22 meters. Okay, so we're going to work in meters for the remainder of the problem. So I need to find the spring constant in order to write my force function, which is required in order to integrate to find the work. So I have to have a function in order to find the work. So the first thing I'm going to do is find K, which is my spring constant. So I'm given some discrete data. I'm told how much force it is to hold a discrete length. So, if you had some machinery, you could stretch out the spring and then measure how much force. So that's kind of what's happening here. This is like empirical data that you would receive. So force equals K times X. So 7 equals K times X. X is the distance from the natural length. So this is going to be the final length, which is this 0.14 minus the natural length, which is 0.06. So be careful about that, right? So I end up with 7 equals K times 0.08, and I get K equals 87.5 newtons per meter. So that is my spring constant. With that constant, I then can write a function for force. So the second thing I'm going to do is write my force function. And that will be f of x equals K, which is 87.5, times X. I know that to be the case because of Hooke's law. I don't have to do any additional work to know that my force function is my K times X. Let's scroll down a little bit here. So we're going to stretch from 0.2 to 0.22 meters. I'll leave that there so we can see. Because then the third step is going to be to integrate to find work. So work will be equal to the integral of 87.5 x dx. Now, we have to be a little bit careful with the limits of integration. We've already converted 20 centimeters and 22 centimeters into the proper meters length. But remember that the x inside our function is the distance from the natural length. Everything needs to be consistent in your integral. So if your x is the distance from the natural length, then the numbers that you put on your limits of integration also have to be the natural distance from natural length. Everything needs to be kind of matchy-matchy. So if I have a and b as my limits here, I need to calculate how far they are from natural because it needs to be consistent with my x value. So this a value will be 0.2 minus 0.06, which was my natural length, which will give me 0.14. And then b will be 0.22 minus 0.06, which will be 0.16. So the limits of integration for my work function are going to be 0.14 to 0.16. Then I have my 87.5 x dx, and that will be what I take my integral of. So when you do the work for that, you can do it either using a technology tool or you can do it by hand. I will get 0.263 joules. So that is a pretty straightforward example of a spring problem. These are pretty common, and I would say that's really the basic example. You're given a natural length, a force to hold a stretch, and then you're asked for the work to find this additional stretch. So that's kind of the basic level. Let's look at a more complex couple of examples. So this first one, I have a spring again. My natural length is 0.1 meters. I'm already in meters, so I'm not going to do any conversions. I'm given my K value, and it is equal to 400 newtons per meter. And then I'm given some other information. So we're going to say that we start at a length of 0.14 meters. Okay, so my natural length is 0.1. So I know I'm starting with this stretch. And then I'm told that 4 joules of work are applied. And I'm asked for the final length. So this is the thing I'm trying to find, is that final length. So when you're given the amount of work at the beginning of the problem, you know you're going to have to set up an integral and solve for one of the two limits of integration. In this instance, because it gives us this starting length, we know it will be the upper limit of integration that we're solving for. But let's go ahead and plug everything in. So because of Hooke's law, I know that my force is equal to Kx, and I have K. So for this problem, I already know my force function. I don't have to do additional work. I can jump straight to setting up my work equation. So work is equal to the integral from A to B of 400 x dx. Now, again, I have my starting length previous to the similar to the previous problem. This is the total length. I need to be consistent, so I need to convert that into the stretch, the distance from natural. So I subtract 0.1 in order to get the distance from my natural length. This is going to be equal to my lower limit, which is A. I don't know B. That's what I'm going to be solving for. So let's plug in what we do know. I know work. Work is 4. I know my lower limit A, which is 0.04. And I know my function. Sorry, B is unknown. I'm just going to put it in there. And then I know my force function. So now we will go ahead and approach solving this. Excuse me. So I have 4. I'm going to take the antiderivative here. So I'll have 400x squared over 2. I'm going to evaluate that from 0.04 to b. So when I plug all of those things in, my b and my 0.04, I end up with, well, 400 divided by 2. So I get 200b squared minus 200 times 0.04 squared. I go ahead and simplify that a little bit, and I get 200b squared minus 0.32. I'm in business now because I have a single equation and a single variable, a single unknown that I can solve for. So I'll add the 0.32 to both sides. I get 4.32 equals 200b squared. I'll divide by 200 on both sides. So I get 0.0216 equals b squared. And then when I take the square root, I get 0.147 equals b. So this is almost my answer. Oh, and I apologize. When you take the square root, you do get a positive and negative number, but we're looking for that positive stretch, so we're not going to worry about the negative number. This is almost the answer, but remember that because everything is consistent, this number value is the distance from natural length. It needs to be consistent with the original Hooke's law, which says that x is the distance from natural length. So that's the distance from natural length, which means that the final length is equal to the natural length plus b. So that will be 0.1 plus 0.147. So my final answer is 0.247 meters. So that was an example we had to solve for the upper bound. Let's look at an example now where we have to solve for the lower bound, for A instead of for B. So in this one, I have a natural length of 8 centimeters. Now, I've already done a lot of problems like this. I am feeling confident. I know that I'm going to need to convert that into meters. So I'm just going to start converting them into meters as I go because I know that my problem is going to be in meters. I know that my spring constant K is equal to 240 newtons per meter. I am going to apply 0.8 joules of work, and I'm going to stretch the spring to a final length of 19 centimeters, which equals 0.19 meters. So I'm applying 0.8 joules of work to stretch the spring to this final length. The question is, what length was the spring at when I started applying work? Okay, so once again, I know that my force function by Hooke's law is equal to K times X, and I know K, it's 240. So I have my force function. I can jump right to plugging everything in for work. So I'll have my integral from A to B of my force function, which is 240x. I know that B, my final length, is 19 centimeters. I need to convert that into distance from natural length. I need to do that because that's how my x is defined. And if my variable is in distance from natural length, my numbers need to be in distance from natural length. Everything needs to be consistent. So I have 0.19 minus my natural length, which was 0.08. So I get 0.11 meters. This is the final length, so this is B. It is my upper limit of integration. A is unknown. That's what I'm trying to find. A equals question mark. We're trying to find it. So I have here 0.8 joules equals the integral from A to 0.11 of 240 x dx. I will integrate and get 240 x squared over 2 evaluated from A to 0.11. When I plug those values in, I get, 240 divided by 2 is 120. So I get 120 times 0.11 squared minus 120 times A squared. So my next line will be 0.8 equals 1.452 minus 120 A squared. When I subtract 1.45, I get negative 0.652 equals negative 120 A squared. I divide both sides by negative 120 and then take the square root. And so I end up with A equals 0.073711. Again, that is the distance from natural length. So in order to find the total length, when I started applying work, I need to add the natural length. So the starting length is equal to A plus natural length. And in this instance, my natural length was, let's see, I'm sorry, I apologize, I just forgot it. 0.08, okay. So I have 0.073711 plus 0.08, and I get 0.15371 meters. Now pay attention to your problem statement. If it asks you for an answer in meters, then you're all done. But if it asks you for the answer in centimeters, then you need to convert this answer back into centimeters. And usually when problems are given, whatever you start with, you're going to want to end with. If I give you a problem in centimeters, I want the answer in centimeters, even though in the interim steps we had to convert. So our answer here is going to be, when I convert back to centimeters, 15.371 centimeters. So that is the final answer to those problems. So that's what I have to say about springs. It's kind of like a more basic problem and then two of the more involved problems. Thanks so much for watching, and if you have additional questions, you can put those in the comments.